So in this chapter, we're going to be talking about matter. Everything you see around you is made of matter. It's anything that occupies space and has mass. And so we're going to be talking about the basic constituent parts of matter and how it behaves and how it organizes itself and why it does what it does. Some of the things I'm going to be talking about may boggle your mind. And you know what? We're just beginning to understand what matter is and what it does and why it does the things that it does and where did it all come from. Because in fact, the explosion of knowledge that happened throughout the 20th century has definitely changed the way we understand the universe, both macroscopically and microscopically. And where we're going with science is to the limits of our imagination. And so let's stretch that as much as we can, just like the universe is stretching itself out, and learn as much as we can about matter. Since matter is everything that takes up space and has mass, you have first to understand what mass is. Now, mass is the amount of matter, or how much stuff something actually has. And we use things like scales to measure that, like the one you see in the picture. And in the metric system, we measure that in grams. Now, the volume is how much space that same amount of stuff is going to be actually taking up. And in the metric system, we measure that in liters, or in cubic meters. And space is measured three-dimensionally in the sense that it has both width, length, and height. But as Einstein would say, space is much more than that. Space is in fact something that's inseparable from time. In that if you actually want to locate something, you don't need 3 dimensions, you need at least 4 dimensions. Because it's not enough to say, I am here. It's not enough to say that I'm here. It's also important to say when I'm here. Because if you were to come back here an hour later, I probably wouldn't be here still. And so that's kind of how it is. You need to know space and time together. And also, it's important to understand space and time as one thing because of the way that space and time act together because of the matter that's in it. Matter changes space and time. And energy changes space and time. And matter, by the way, is energy, and energy is matter. Yet that's a little more complicated. We'll talk about that in a second. But first of all, what is matter made of? Matter is made of tiny little particles. Everybody knows about atoms, and some people might even know about the things inside of that. Electrons, protons, neutrons. But even those things are made of smaller things even. Fundamental particles we call fermions and bosons and quarks and leptons and things you probably never even heard of before. And so that's the kinds of things we have to talk about in this lecture series. Now in science, we establish a relationship between mass and volume that's called density because it tells us a lot about the particle of matter that we're talking about, since you're basically telling not just how much stuff that particle has, but also how much space it's taking up. And since that's the definition of matter, we have to talk about it in terms of density. Now density is basically the mass of the object divided by the volume it takes up. And just like any other fraction, if you were to increase the top of that, you would increase the density. But if you increase the denominator or the bottom, you will decrease the density. And so if you have more stuff in the same amount of space, you make the object denser. But if you have less stuff in the same amount of space, you're going to make the object less dense. If you have more volume for the same amount of stuff, you make the object less dense. If you have less volume from the same amount of stuff, you make the object more dense. And these are concepts that most people do understand. Now remember, the density of water is 1. This means that any object that has a density above 1 will sink in water, while any object that has a density below 1 will float on water. And it will float higher and higher on the water, or less and less of it will be underwater, the further apart it is from actually being at 1. If you're exactly 1, you don't sink or float, you are within the water. As you increase the density of an object, you make more and more of it sink until finally it sinks completely if the density of the object is above 1. Which tells you, for example, things like boats must always have a large volume to make up for the large mass that they have to carry, so that their density is always above 1. And when you get multiple liquids and you put them all in one vial, they will organize themselves in the order of density, just like you see in the picture there. Which is, by the way, what explains things like, for example, the differentiation of the inside of the Earth, because of that density differences. It also will explain a lot of convection on the Earth, how the winds are moving in the Earth, how the magma moves inside the core, how the plasma moves inside the sun. It's all because of density differences. Also remember, just because, that when you warm up an object, you basically accelerate the molecules, making them spread out, which makes the volume larger, and therefore it increases the denominator, making density go down. But if you decrease the temperature, you're going to decrease the denominator and making density go up. So colder objects tend to be denser than hotter objects are. There are some exceptions, of course, like water, for example. When it freezes, it actually expands. But it does that because when it freezes, it becomes a crystal and it actually expands. And we'll talk more about that when you hit biology and we'll talk about properties of water. So that's density. And remember, if you're less dense than water, you will float on water because the buoyancy force of the water will be greater than the weight of the object that's sitting in it. Another interesting thing about matter, it is actually the same thing as energy. Energy is matter and matter is energy. This is something that Einstein thought of based on the work of many scientists that came before it. You see, people were trying to understand how light behaved. And some people thought light behaved like a particle. And that was an idea that was as old as Newton's idea of light. But since Newton, in the 17th and 18th and 19th century, people studying light properties saw that it worked more as a wave than a particle. But then other scientists realized it's more like it's both a wave and a particle. It's kind of like a duality thing to it. And so Einstein, trying to conciliate that problem, studied the properties of light and matter, and actually understood that there was no difference between light, which is a type of energy, and matter, which is a mass. Mass is basically energy that's organized itself so compactly in one space that it actually becomes tangible or touchable. At its core, matter is actually made of fluctuating energy particles, which we call fundamental particles called fermions, such as quarks and leptons. And what gives matter its actual consistency, it's a fundamental particle that's called the Higgs boson, which we're trying to find right now in particle accelerators. And we'll talk about that later. But what you need to understand about this is that energy is matter and matter is energy. There is actually no difference between matter and energy. And in fact, most of the universe is empty space, but not empty energy. The universe is full of energy. In fact, it's energy, dark energy, that's accelerating the universe, making it expand faster and faster, like we talked about at the beginning of the year when we did space. And then, other than that, you have a lot of matter that you can't see, matter that's not detectable, which is called the dark matter, such as the matter inside of black holes and other things like axions and matter that won't shine. And then finally you have the intergalactic gas, which is the majority of the stuff that's out there, and it may not be visible because it's in the dark. And then you have to find a shiny matter or matter that's reflecting light, which is what you actually can detect. But all of that matter, whether dark, intergalactic, not shiny material, or actually material that actually emits light, all of this material is actually energy at its core. Energy that's trapped in matter by a mystical particle that we call the Higgs boson. And we'll talk about that later. Now, just to make this visual for you so you understand what I mean by the energy being matter and how much energy is in matter, think about this. Einstein came up with the actual relationship between energy and matter based on his work with light particles, and he identified that energy equals mass times the speed of light squared. Now, the thing is, the speed of light is 300,000 kilometers per second. So that's 300,000. That's 300,000 kilometers per second in meters per second, which is what you actually need to do in this equation. You have to add 3 more zeros. 3 more zeros. And now you have to get that number and you have to square it. Let's put that in scientific notation to make things really clear. You got 1... Okay, let me just see here. So you put a dot right there and then carry the dot over. So 1, 2, 3, 4, 5, 6, 7, 8. So that's 3 times 10 to the 8th power. That's the speed of light. Now, if you actually, in meters per second, if you actually get there and you square that, well, you do distributive properties with the quotient, and you're going to get 9 times 10 to the 16th power. All right? So, even if your mass that you're talking about here was 1 gram, 1 single gram of mass, a tiny little gram, you wouldn't even feel if a gram of mass fell on you. It's very, 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 very small. But 1 gram of mass would have this much energy in it. Now, how much energy is that? Well, write it out. Let's see what you got. Let's write this out. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 zeros. Let's see. Let's group every 3 And let's see what we got. Thousands, millions, billions, trillions, quadrillions. That is 90 quadrillions. Holy crap. That's amazing. 90 quadrillions. 90 quadrillion units of energy for every gram of matter. How much matter do you have? I'm about 80 kilograms or 180 pounds. But look at that. 80 kilograms. 80 kilograms is 80,000. 80,000 grams. So you get this number and go ahead and add 3 more zeros next to it. Alright? 3 more zeros. Add another 0 from the 80 here. So you go another 0. And then multiply 8 by 9. 8 times 9. You know that trick that you do this with the hand to go 1, 2, 3, 4, 5, 6, 7, 8. It's going to be 72. So that would be 72 with then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 zeros afterwards. Group every 3. Let's see. Thousands, millions, billions, trillions, quadrillions. Oh my gosh. Quintillions, sextillions, 7.26 stillions of energy. That's how much energy I got. No wonder I'm crazy. I'm full of energy. If I were to disintegrate in a matter-antimatter collision and every single one of my atoms were to release its energy that's inside of it and become pure energy, that will be enough energy to destroy the entire solar system. So next time you say, I've got no energy, think about it. You're made of matter. You're full of it. Aha! So the universe is full of energy. Much of it is free as dark energy. Much of it is trapped as dark matter or actual matter you can see. But the universe is made of energy. Some of that energy is trapped as matter. And that's what we have to talk about. So in the next video, we're going to start covering about what is this matter you're talking about. And what's the matter with it?